Moving right along in our analysis of waves to a couple of things called beat frequencies and Doppler effect. Beat frequencies are a pretty simple concept. The idea is if you have two waves that are interfering with each other, the ones we looked at were kind of simple situations where we had a crest moving this way meeting a crest moving this way, and it made a bigger crest. Or if we had a traveling wave moving this way meeting a traveling wave moving that way, then we got our standing waves by doing that. But in this case, the frequencies of the two waves had to match. But what happens if you have two waves with different frequencies is you get them constructively interfering and then destructively interfering at different points in time. And you can hear this kind of beat frequency superimposed over the two other frequencies. The equation for beat frequencies is nice and simple. All you do is subtract the two frequencies, and that's the rate at which you'll hear this kind of ringing superimposed on the other frequencies that you have. So let's look a little more closely at what's going on with that. Here it is. So here I have two different waves, and they have slightly different frequencies. One is a 15 hertz wave, the top one, and the green one is 14 hertz. When you combine those two waves, you'll notice over here the crests line up with the crests, so you get constructive interference, but here the troughs line up with the crests, you get destructive interference. If we start this little animation, you can see that better. So this is showing where you're at in each wave at a given point in time, and then the total wave. So here they were kind of canceling out. Now they're not canceling out as much, and now they're starting to build. And in the middle of this wave packet, you have crests lined up with crests and troughs lined up with troughs, but they won't stay that way, so you end up with something like this. If the waves have frequencies that are more different than just one, let's grab this guy, then you get some different wave patterns, but it's still a repeating pattern where the frequency is given by the difference in the two waves. Might not look quite as nice and pretty, but you get the idea. Okay, let's listen to some of these. So here we have we can't do 15 and 14 because that's out of the audible range. So if we go 200 and 201, we'll go ahead and play this sound, and we would expect there to be a ringing on top of, looks like the other video I was processing was done. Alright, there should be a ringing kind of superimposed on the sounds. So I don't know if that volume's loud enough for you or not. So you hear that kind of woo sound. Now we can go ahead and move, actually let's move it to same difference but a higher pitch. So we hear a higher sound, but we still have a ringing that is ringing once per second. Now if we make the difference a little larger, let's just go to 2 now. Come on. Try my mouse, the tab's not working. Okay. Now that ringing is twice as fast. And now it should be 3 times a second. And eventually it's so fast, I mean, you can't really hear. Guess I didn't need to switch that one. You can't really hear it if it's way fast. It's just kind of warbling. So frequencies that are off by a significant amount, they don't really have beat frequencies. This is kind of a phenomenon that we consider for frequencies that are close to one another. Okay, moving right along, that's really all there is to beat frequencies. Calculations are going to be nice and simple. Now the Doppler effect might be something that you've heard of. If you've ever had a car drive by you and noticed how the sound seems to be higher pitched when it's moving toward you, and then when it passes you, then the pitch drops. Maybe it's more distinct with like a motorcycle or if a siren is going. That is what we call the Doppler effect, and it happens with all waves. It's a big part of astronomy actually, because it causes light waves to shift if the sources are moving toward or away from you. And that's one of the big tools for figuring out how fast things are moving in space. But we're mostly going to focus on sound waves and the Doppler shift, or the Doppler effect in sound waves. So the idea is, if you have some source of sound, in this case the siren on a fire truck, and everybody is at rest, then you will all hear the same frequency. These waves will hit you with the same frequency as they hit this person, as well as the person sitting inside the truck. But now if the truck is moving, it's going to release one wave here, but then it moves before it releases the next wave. So it kind of was chasing after the wave in front of it here. So these waves get all bunched together. So an observer here in front of the truck, they're going to hear a higher frequency because those waves are going to hit their eardrums more often. The person behind the truck, since now the waves are getting spread out because the truck moves further to the right before it releases another wave, they're going to hear a lower frequency. Somebody inside the truck would hear no change at all because they are moving with the truck. So you have to have relative movement between the source of the sound and the observer. Okay? And that's kind of what I already explained. One other piece of information, though, is because the sound wave is traveling through the air, that becomes a frame of reference. So I know we were in relativity mode for so long that it's like, oh, well, we could say that they're at rest, or that the truck is at rest and they're moving toward them and whatnot. Here, you can't really do that because basically you want to think about whether something is moving relative to the air or not, because that is what the wave is traveling in. And as we'll see in some of our calculations, you'll get a different amount of Doppler shift for the truck moving towards this observer versus the truck being still and the observer moving toward the truck at the exact same speed. In both cases, the frequency will get higher when they're moving toward each other and lower when they're moving away, but the amount by which it shifts up or down depends on which of the two things is moving. I have a couple of animations here, just kind of giving you another feel for the Doppler effect. So here's a stationary source, and you can imagine these waves propagating out in all directions, and it doesn't matter what side you are standing on relative to the source, you will hear the same frequency. Now here the source is moving, so you can see the waves in the rear get spread out and in front get bunched up. On the sides it's a little more complicated. We won't do any calculations with those types of things. Okay, here's a quick little derivation for one of our Doppler formulas. We're going to have several Doppler formulas. Sorry about that. But if we imagine that there is some stationary observer, Mr. Stickman over here, and there's a source of sound, could be that fire truck, doesn't really matter, that's emitting sound waves and moving toward this observer. So this is the location at some time 1, and this is the location sometime a little bit later. And so this here is the first wave that was emitted back when the source was at location 1, and then when it's at location 2 it emits another wave, and so the wavelength, effective wavelength for this observer is contracted from, if it wasn't moving, the wavelength would be this entire distance here, right? So we can do a little calculation to derive a formula for the frequency that this guy is going to hear, and we call that f prime. Again, it's not a derivative, it's just the shifted frequency as opposed to the frequency if this source were at rest. So first let's look at the shifted wavelength. This would be the total wavelength, this line I drew here. But because we moved here, the wavelength is only this little distance here. And we can calculate what that is. If we call this here d, the new wavelength is going to be that total distance minus the distance that the source moved, which is this distance here, from there to there. Okay, and the distance the source moves it's equal to its velocity times the period of the wave, because that's the time in between when the first wave was emitted and the second. So that's the travel time between those two waves. So we've got this situation here. Now the period is equal to the inverse frequency, right? And frequency is equal to v over lambda. So if we plug that in for period, lambda over b, because it's v, because it's inverse frequency, we get this, being careful to label what velocity we're talking about. This is the velocity of the sound wave. This velocity here was the velocity of the source of the sound. Then you can factor out a lambda here. Now this is the original unshifted lambda, and you get this guy here. And we didn't want to know the shifted wavelength. We're often concerned with the shifted frequency. So this is our expression for our shifted frequency. And if we plug that into speed of sound over shifted, sorry, not frequency, wavelength. So if we want to find the shifted frequency, we plug in sound over shifted wavelength, and that gives us the original frequency over 1 minus source sound, blah, blah, blah. Okay? So there is one equation that we can use, and you can follow a similar process to get 4 different equations, all big and unruly, for 4 different situations. Source is moving and the observer is stationary, and they're getting closer together. If they're getting farther away, it's the same equation, but now we have a positive sign here instead of a negative sign. If it's the observer that's moving and not the source, then you get this guy here, again with a positive and positive if you're moving toward. I guess it wasn't positive there, it was negative, but the sign switches for a change in direction. Now, if you like writing down all 4 of these equations and plugging into them, that's fine with me. I tend to not like that. I like using this one equation here, because first of all, I only have to remember one thing. It is even bigger and uglier, but there's 1 instead of 4. And also this takes into account if both things are moving, whereas these ones don't really work that way. I guess you could find one and then plug it into the other or something, but here we go. You can have moving observers or sources, one or the other or both, and everything is good. Now to figure out the signs, you'll notice I've got a plus or a minus and a minus or a plus, and that's not a typo. If the objects are getting closer to each other, even if they're both heading in the same direction, so there's like one car speeding away, and say this guy is going that way at 20 meters per second, and the other guy is catching up because they're going 30 meters per second. Even though this guy's going away, the distance between them would be closing. So if they're getting closer to each other, then you use the top signs, which is the plus and the minus. And if they are moving away from each other, the distance is growing, then you want to use the negative for the numerator and the positive for the denominator. And just to end with something a little bit fun, further explanation given by a professional physicist. You can click here to see the nice little video clip. Alright, see you next time.